Now, we've talked about why chemicals separate, but we haven't discussed getting a good separation in a reasonable amount of time. Notice that in this case, for example, two of our chemicals are coming out right on top of each other. That's why this peak looks so strange. Over here, three of them are close enough together that they're all blending into this strange looking peak shape. In other words, our resolution is quite poor between those three species. So how do we get a better separation? Well, in a previous video I mentioned that the temperature of the column matters. Lower temperatures allows for everything to move slower, and thus it allows for everything to separate out better. Of course, if some chemicals that take longer to elute travel through this column too slowly, well then our run might be impractically long. So let's more clearly illustrate the issues with a visual, and then we'll also discuss the solution to the problem. And the solution is going to be to develop what's known as a programmed temperature ramp, which I will contrast with isothermal, i.e. constant temperature situations. Imagine we have a mixture of three compounds, and let's say they're all the same polarity, so the only distinguishing characteristic is the boiling point. Two of them relatively low compared to the blue chemical. Quickly ask yourself, what should the order of elution be for these three chemicals? You should have thought that since polarity differences aren't a factor, it'll just be based on boiling point. Smallest first, then green in the middle, and then blue last. So let's say that we run these three through a column at 50 degrees Celsius, so a low temperature. Here's what's going to happen. The red travels the fastest, makes it out, there's our signal, green comes out, and yeah, way too long. Okay, so let's get that blue chemical out a lot faster. Let's raise the temperature to about where its boiling point is at, so 135 degrees Celsius. And let's run it now. Well, the good news is that the blue traveled a lot faster and it came out in a reasonable amount of time. The bad news is this temperature was so much higher than our red and green chemicals' boiling point that there is little distinction between the speeds that the two traveled through the column. The red still did technically make it out first, but this is terrible separation, awful resolution, and not at all easy to analyze. So what do we do? Well, the solution is to actually create what's known as a temperature ramp, and if you're in 2124, you had the pleasure of doing this during GC1. We start at some lower temperature, maybe a bit higher than this, but still relatively low, so that these can travel at reasonable enough speeds that they make it out quickly, but not so fast that they just come out on top of each other. And then we ramp the temperature. We program the oven to increase to a higher temp of, say, 125 degrees Celsius, and that's going to allow for our blue solute to finally elute out the column at a relatively quick pace. So let's see this in action. Red comes out, green comes out, boost the temperature, blue speeds up, and it also comes out. And now we have the best of both worlds. We have good separation between green and red, but we also got the blue out in a reasonable amount of time. It kind of reminds me of the story of Goldilocks and the Three Bears, and if you don't know the story, don't worry so much about it, but if you do, you should remember she finds these three porridges, one's too cold, one's too hot, and the other is just right. But in this case, just right doesn't mean it's in between these two temperatures, it means it starts cold and then goes hot. From here, let's just summarize everything with some notes. Temp program. First, let's address the issues. At low temperature, or at low T, high BP solutes take too long to elute. At low T, high BP solutes take too long to elute. At high temperature, or at high T, low BP solutes exit the column at similar times. Low BP solutes exit column at similar times. The solution start at a low temperature and ramp to a higher temperature. Solution start at low T, ramp to high T, and we call that temperature programming. Now some of you may be thinking, rather than go through this ramping process, couldn't we just keep it at a constant temperature but find some middle temperature in between these two, like maybe 85 degrees Celsius, and wouldn't that give us a good enough separation in a quick enough amount of time? And the answer is maybe. It depends on what's in the mixture. Let me end the video by showing you an example where it would not work very well to find some middle temperature and just hold it there the whole time. In the example I'm about to show you, a mixture of alkanes, very basic hydrocarbons. If you took organic chemistry, you should recognize this formula. But really quick, these compounds contain some number of carbons and then a little bit over twice as many hydrogens. And this particular mixture had alkanes that had as few as 6 carbons in them to as many as 21. And the more carbons, the bigger the molecule. The bigger the molecule, the more of those van der Waals forces we had. Thus, the higher the boiling point and the longer it would take to get out of the column, i.e. the higher the retention time. Now, a very nice separation of all of the alkanes was achieved when the column was run with temperature programming. In this case, they started the column at the low temperature of 50 degrees and then gradually raised the temperature all the way to 250 degrees Celsius. Now, they didn't just jump straight from 50 to 250 in an instant. They gradually raised the temperature at a rate of 8 degrees per minute. And again, that achieves a very nice separation of all the compounds within a little under 40 minutes, which isn't bad. On the other hand, when they ran this mixture through the same column, but just left the temperature at a constant 150 degrees Celsius, right in between these two temperatures here, this is what we got. The smaller, lower boiling point hydrocarbons came out almost on top of each other, and the larger alkanes take longer and longer and longer to elute. This 15 carbon alkane takes 90 minutes to make it out. Who knows how long the 21 carbon alkane is going to take. So ultimately, the intermediate temperature is not the way to go for this mixture. But the programmed temperature ramp, that works very nicely. Now, I'm going to end the video here, which means I'm going to end the semester here. So, bye everyone. I wish I could have interacted with you better, but hopefully these videos were helpful, and I wish you the best. Wait, I still need to write a final exam.